The number of radioactive atoms remaining after T days of some element is y equals y sub 0 e to the negative 0.005 t, where y sub 0 is the initial amount. Find the half-life. We can do this a couple of different ways. First, we have y sub 0 e to the negative 0.005 t, and we can set it equal to our half-life equation, which would be y sub 0, our initial amount, times 1/2 to the t over k, where k here is our half-life, so we'll say t equals the number of days, and k here is our half-life. So we can see that we have y sub 0 in both of them. We can divide it out. Then we can see this as the following: e to the negative 0.005 raised to the t equals 1/2 to the 1 over k to the t. Recall also what we did today in problem number 2. We had very similar to this when we were solving for e to the k. Since we have both exponential forms to the power of t, that means these bases, the inside parts, have to be the same. So we have e to the negative 0.05 equals 1/2 to the 1 over k. Now we're trying to solve for k, so let's take the log of both sides. We'll get negative 0.005 equals 1 over k ln of 1/2. We need to move the ln to the other side, so we'll have 0.005 again over ln of 1/2. I'm going to go slowly on this so I don't lose anybody. Now we have two fractions are equal, their reciprocals are equal. So we have negative ln of 1/2 divided by 0.005. Now if we were going to use a calculator, we just type it in right now. Let's say we didn't have a calculator. We could simplify this because recall ln of 1/2 is the same as ln of 2 to the negative 1. So if we take that as 2 to the negative 1 divided by 0.005, that negative 1 can come down, which will make it positive. So if we had no calculator, we could simplify it to something like this. Since we have our calculator, just type it in and we get approximately 138, let's see, 2.629 days is our half-life. This is not the only way. We could call this one method 1. And in some ways it's good to have those skills to be able to manipulate like this, but we could also take a look at another one and we could just call this method 2. And perhaps method 2 is a little bit easier. We would have 1/2 y sub 0 equals y sub 0 e to the negative 0.005 t. Since we're going to say that here's our amount, we have our initial amount, we want to find the time it takes to be 1/2 of that initial amount. So we can divide by the y sub 0's, and then we'll have 1/2 equals. At that point we can take the ln of both sides. ln of 1/2 equals negative 0.05 t, and that's looking an awful lot like this step right here. So we would have ln of 1/2 divided by negative 0.005, and we don't need to go through all this same work again. At this point I'll just write the approximation that 138.629. In this case, the amount that we're solving for, this t, This will be days, and this is our half-life. Now let's take a look at part B. Move this up a little. A sample is no longer useful after 95% of the initial amount has disintegrated. How long will the sample last? Well, what do we want to find? If 95% has disintegrated, how much do we have left? 5%. So we want to see how long will it take us to get 5% of our initial amount. Y sub 0 e to the negative 0.005t. And at this point, this is a fairly easy one. Divide by y sub 0. We'll have the ln of 0.05 equals negative 0.005t. And we'll have ln 0.05 over negative 0.005. Do this on our calculator. And we'll have ln of 0.05 closed divided by negative 0.005. And we get, can't really see that, there you go, 599.146. So this would be 599.146, or, this is our approximation, or about 599 days that this sample would be useful. And we're done.